Okay, morning. Yeah, so this is our final day before we get into the midterm exam. First thing I probably should mention to everyone is our midterm starts actually at 9:20 instead of 9:30. Okay, that's the same as the first midterm. So make sure you come here on time, otherwise you lose your own time. Okay, so the midterm exam is the same requirement as the first one. That means you have one cheat sheet, double-sided. You can print it or you can write it, whatever. That's all the assistance you have. I assume you do not need a calculator because we will not need to calculate anything. Okay, more on the concepts. The coverage is after midterm. That means we start from the text mining, then we get into final section on the classification. So that's the coverage scope. I'm not sure whether you have other questions, but I probably should give you a few minutes before we go to the presentation survey. So if you have any questions regarding to the midterm exam, better, you can raise it now. Then we probably can have some discussions instead of you come to my office because likely those questions are of general interest. Okay. Any questions related to the midterm? Okay. Yeah, if there's no question, I assume, you just remember come earlier, okay? 9:20 instead of 9:30. Okay, we finish at 9:50, so total 90 minutes. Okay, the number of questions is similar to the first midterm exam. I assume you should write somewhat fast, and write concise in the sense you answer the key points instead of keep writing, try to compose very long sentences. Okay, so let's start our presentation on the surveys. So for the survey, our TA group actually finally selected a group of survey for us to enjoy, to see what is the good survey composed of. Last lecture I was out of town, so the TA was in charge. So we got into like 4 or 5 surveys. Today we have 4. I think we're probably following the order in this particular order organized by the file names. Okay. So I think the first one. Okay, let's see. We just save this link. The first one will be Yujia and Youshan Zhuang. So make sure. I think you both can come and and doing the presentation. Okay. Okay. So you can. I think if you want, maybe we can use both. Hopefully, both will work. Those will work. Yeah, I have to go back to bring the attendance sheet. I did not bring the attendance sheet. You can just start. Okay. Yeah, thank you.
Hi, everybody. So today we're going to give the presentation about the recommendation algorithms. So what I did is that as you know, recommender systems plays significant roles in many websites because a lot of websites are depending this to give recommendations and make profits. So there are a lot of recommendation algorithms. So the most basic ones are based on clustering and classification, and they have some other basic recommendation algorithms. So there are association rules, collaborative filtering, content-based filtering, and then we're going to introduce the structural data. So I believe most of you have already been very familiar with clustering. So it is given a data set, and the algorithm is going to automatically group the data into several clusters. So in each cluster, the data themselves are more familiar with each other. But this similarity is not based on your criteria, but it is just automatically. So it is mostly unsupervised learner. So then we're going to have classification. So this one, unlike clustering, is a supervised learner. So this algorithm is going to give you the classification and generate the classifier according to your criteria, so that the classifications themselves are more likely to fit in your groupings. So then comes the traditional data mining, the association rules. This idea is based on this problem. So figuring out the probability of the transaction of one set of products A, given the fact that we already have a transaction of the set of products B. So that's a very clear example. So if the customer bought ping pong paddle, so you can assume that he is more likely to buy ping pong ball, so we can give recommendations accordingly. So there are two concepts in this association rules. The first one is X means a set of products, and Y means another set of products. So there are two concepts to determine what are the associations among these two set of products. The first one is support. So you can see the occurrence frequency in the rule. If this rule is repeated again and again. So the second is confidence. So if this is a very strong implication, if I'm gonna buy a ping pong ball paddle, am I gonna be more likely to buy a ping pong ball? So these are two important concepts. Then the collaborative filtering. This is very important and very widespread used. So the basic idea is that the like-minded users are more likely to have the same interest on the same set of products. So as you can see on the image there, so the two users on the left, if they have the same interest in ice cream and maybe apple pie, they're more likely to have the same interest in food, some other products. So the similar can be applied to the users on the right. So there are two major categories on this. There are neighbor-based algorithms, and there are model-based algorithms. Model-based algorithms are more complicated, but they are more mathematically generated and more convenient. So there are also drawbacks from collaborative filtering, because you also need to explore dislikes and unfamiliar items for everybody, because maybe you are not just don't like them, you just don't know it, so you didn't mark it. So then we come to the neighbor-based algorithms. Neighbor-based algorithms is widely used. It is a key component of collaborative filtering. So it is very influential, popular, intuitive, and it is widely used, like in Amazon.com. But we have some improvements on this neighbor-based algorithms, like weightings. So because similarity is not everything, we need to give weightings to the neighbors. So the first one is similarity weightings, which means that if a user is a better predictor, we can give this predictor higher weighting. The second one is significant weighting. So if we have more correlated items, it should be given higher significance. The third one is variance weighting. So it doesn't mean that if two users have similar ratings on the same one, they are more similar, because everybody gives high ratings to Titanic. So the Titanic, this product is not a good predictor, but the ratings varies a lot in the movie Sleepless in Seattle. So we should give higher ratings to the second movie. So this widely used algorithm also has some drawbacks: the sparsity and scalability. So the sparsity means that most users only interact with a small number of items from the database. Like in the Amazon, users only maybe buy less than 1%. So you may not get good predictions based on this. And the scalability means that nowadays more and more data are existing in the databases. So running this algorithm takes longer and longer times to do the computation. So this one is content-based algorithm. It focuses more on the user item pairs. It doesn't focus on the relationship between the users, but it gives recommendations according to your preferences. Like some websites already apply this method, like in the Pinterest. After your registration, you are asked to follow 5 topics that you are very interested, and they are giving you some recommendations. So this process is not only just at the very beginning, but also throughout your using of this website. For example, if you're using the Pinterest, you're always you can select your interest by just click on the pin it on the right image, so that the system can dynamically update your recommendations based on your users' interaction with this website. We have some sort of implementations, and there's one thing that worth a reminder is that there's a highly cited paper, GAT5, which is a good combination of a content-based and collaborative filtering algorithm. So give recommendation based on both of these two algorithms. So there are also some other user-centered recommendation algorithms, like the website can keep record of your clicking behavior or your tags.
All the previous data that we mentioned for the recommendation system is unstructured data. And actually, there can be structured data to make it more systematically analyze this recommendation. So the structured data can be homogeneous information network, and more complex is bipartite network and even heterogeneous information networks. So there are many similar definitions, and especially the common neighbors that have been mentioned before, and it can be applied to the traditional ones, but there are more others that can be extended, like especially some specific similarity definitions can be used in structured data. So we'll see that one by one. The first one is correlation. The correlation is the extent of two variables that can have a linear relationship. So it is the most accurate in terms of a linear relationship. It's sensitive to the data distribution, but it also has some limitations. The first one is that the relationship has to be linear. It cannot apply to some curved relationship. And also, it is meaningless for correlation between different node types. That, for example, if a user, like an author, has several papers, but for example, another one is like a book or a paper. It cannot really be compared by different features. So, and the third one is to ignore, it ignores the accurate values, but only compare the relative values. For example, the Pearson correlation. We can see in the right side is the equation. It is good for data from users who may have different rating scales, because it's actually use each x and y are nodes, and minus is average, their averages, and normalized by their normalized by like their factors. So actually, they do using Pearson correlation. We don't have to care about the different rating scales. It's really good for people who like rate for for example, for the Amazon. So someone really likes to give 5 scores, and someone just normally gives 3 scores. So Pearson correlation is really good used for this situation. And there are some extension for the Pearson correlations. It's Spearman rank correlation and Kendall's tau correlation. Actually, they just substituted ratings in the Pearson correlation with rankings and the relative rankings. They are just for easy to it's a cleaner way to you don't have to convert the ranking their exact scores to the a probability. So it's an easier way to show that. And the next one is cosine similarity. As we can see that the cosine similarity is the dot product of x and y and divided by their length, magnitude. So it's really good for sparse data. As we can see that if x and y, some element in x is a vector and y is a vector. If there are some elements are null values, like in the x and y, and we can simply take them as 0, and this equation will ignore the null data. There were no impact for the null data in the cosine similarity. So the next one is the common neighbors. Just like what we have said before, is proportional to the number of common neighbors they have. So the first one that I want to talk about is the Jacob's coefficient. Is the fraction of common features of x and y to the total features that are related to x and y. And there's another one is called Adamic ARDA. It's the sum of each common features divided by their features log frequency in the entire graph. This algorithm based on 2 statements. The first one is the similarity between 2 people, x and y, should be proportional to the number of common features they have, just like what the common neighbors are. But the second one is define the majority shares the most popular features and neighbors. This statement is especially used good for the social phenomena, and in the later we can prove that this algorithm is really good just because of this statement, and it has more it's more accurate than other algorithms. And the third one is preferential attachments. It's the probability of a new edge of node x is proportional to the current number of neighbors of x. And the sim rank, we have already know that is ranking the similarity of nodes and xy by their neighbors' similarity. It's like a second order, because rank their neighbors' similarity. And the heat sim is an iterative sim rank iterative version of sim rank. It used the average similarity score of nodes pointing to x and the nodes pointed from y. The third category is the path count. The path count just takes all the paths in the graph into account, so it's specifically used for the graph structure data. And the first one that needs to mention is the CAS, a weighted or unweighted algorithm. So it is the sum of paths multiplying their corresponding parameters, where each path has a unique length. Note that this algorithm is really limited to that each path must have a unique length. And each parameter exponentially reverse proportional to the length of the path. So, and for the unweighted one, the similarity score will be the path having the same length taken as the unweighted one is calculated by taking the paths as weight 1, and for the weighted one, just taking different paths and adds weight 1 to the different to the total weight. And the path sim, as we already know, is twice number of the paths between x and y, and normalized by the number of paths between node x itself and the number of paths between node y and itself. So it's also a normalized version. The fourth category is conditional probability. The first one we already know. The random walk is a stochastic process to approximately generate a probabilistic distribution. So it's repeatedly randomly choose a neighbor to move in each step, and it actually makes the assumption that the visited possibility is the possibility to be visited in the future. And the page rank is based on the random walk, so it's a use random walk with the probability to returning to the start point at each step. It uses an extra stationary probability to decrease the decrease the sensitiveness to the nodes far away. So this is the benefit of PageRank. And but however, this also has a limitation in recommendation system that it measures only the importance of a node in the network. That means it's only recommend popular items, but not recommending items for specific tastes, like for specific user use. There is one that more more customer to the users. That is PageRank, personalized PageRank that we also learned in this class. It uses the biased parameters with a teleport probability that each step to teleport to a node of its own interest, and thus affects the final probability distribution according to the user's needs. So this one just teleport to other points instead of like a user's requirement, instead of just simply teleport back to the original nodes. And there's also heating time and commute time. Heating time is the expected number of steps required from X to Y, and commute time is just a symmetric version of heating time. That is the sum of expected number of random steps from X to 1 and also from Y to X. And there is a normalized version of heating and time and commute time. As heating time from Y to X is always small if Y has a large number of neighbors, no matter what X is like, no matter what the degrees of X is like. So the normalized version of heating time and commute time is to multiply the score with the stationary probability to avoid the previous situation. And the heats is a relative score based on ranking, is used as iterative precise. And the ranking of the nodes, as we know, is based on this authority score, the sum of hop scores of nodes that points to the current node, and the hop scores, the sum of authority scores pointed from the current node. So it's like a iterative version and also has both directions. And another one is unseen diagrams. It also has a weighted and unweighted version. This algorithm first computes similarity score using either the CAS measure or common neighbors, and then the unweighted similarity score is derived from the number of Y's neighbors that are within K most similar nodes of Y, and weighted is just the sum of weight of each Y's neighbors that are within K most similar nodes of X. So we can see that this algorithm actually combines several things like CAS measures, like common neighbors, with the ranking. And there's also like statistical relation learning that's actually learn similarity score with using classification. There can be many possible models, and in some papers there have Bayesian network, Markov logical network, and probably similarity logic has been used as models for statistical relation learning, just to learn what the weights of the similarity score. So there are also a lot of other combinations, like for between the ranking and clustering, and also the previous really basic similarity definition. So, but we only just not currently we just introduce these basic ones. And this is from a paper, the link prediction problem for social networks. And the result of their experiment is that we can see that the common neighbors always has a really high quality. And the best one is actually academic adder, the one that that's saying that the most popular ones are what people like to be recommended. However, all this algorithm actually have really low raw scores. As we can see, all these values actually just actually is a multiple, like a multiple score of the probability of the random prediction, but not actually the raw score. The raw score for this are always around about 6% to the 10% for even the common neighbors and academic adder. And cases also has good quality for specific parameter. So the last one, I'll just talking about the structured data link prediction. Link prediction is really popular for the structured data. There are two types of prediction. One is atom, person. We can see that all similarity definitions in homogeneous network and techniques in homogeneous network can be directly used here. Just compare like the similarity between atom and atom, and Next one, just the atom person prediction is different type prediction, like to use atom to predict person. So there can be two stages of prediction and one stage prediction. The first stage can be the user-based top-end recommendation and atom-based top-end recommendation. The user-based is just recommended using similar people's recommended atoms, and the atom-based top-end recommendation is recommended using similar atoms. And the second stage is to use the techniques of either ranking, clustering, classification to obtain the most possible atom-person person edge. Yeah. So, but it also has a limitation. When the joint distribution of an atom set is different from the distribution of individual atom set, the results are not optimal. Actually, this happens to a lot of algorithms. And for the one-stage prediction, it just used the metapath-based prediction to select the most possible metapaths, and they use classification regression to obtain the final possibility distributions. Actually, currently there are a lot of papers on mixing different ways to do it, and we're just here just talking about the most basic one. And yeah, thank you.
Okay. Yeah, thank you. I think the survey is very comprehensive. It's very good. For the future, we got to control the time because it's a little longer than we expected. It's good. It's very good. So let's move on. We will get our second one. Second one is on the, let me see. Second one is Amin and Aditi. Okay. So based on the time, I think everybody, we should try to control to 15 minutes. Okay. 15 at most 20, but I think if you finish in 15, that's the best.
So as Amin mentioned that our cluster-based metapaths can be used for link prediction problems. So we'll go over some current state-of-art algorithms for link prediction. So first of all, let's define what link prediction is. Given a network G, where V is the set of various kinds of nodes and E is the set of like various links. So in conventional link prediction methods, what we do is like we train a model based on the known set of links to predict and apply to the potential links. So to predict what the links will be between them, their labels or their existence probabilities. So link prediction can be divided into two parts: link prediction in homogeneous networks and link prediction in heterogeneous networks. So for link prediction for homogeneous networks, first one is the unsupervised link predictors, in which local neighbor-based predicators are used. So local neighbors-based predicators depends on like local information, that like if we have a set of nodes U and V, and we have let's say that we denote the neighbors of U as gamma U and we denote the neighbors of V as gamma V, then the local neighbor-based predictor looks at these neighbors to predict the link between the node U and V. So there are many proximity measures that can be used, which are listed as follows. So one is preferential attachment index. So new users are more likely to link to users who have large number of connections. So the second one is common neighbors. So the common neighbor, it uses the number of shared neighbors by both U and V. So it's an intersection of the neighbors of node U and node V. The other proximity measure is atomic index. So it gives the atomic index gives like each common neighbor of user U and V an importance weight. Similar is the resource allocation index, but the weights given by these two measures are different, as it can be seen in the formula. So apart from local neighbor-based predicators, there are global path-based predicators. So the local neighbors depends on the users' neighbors' information to predict the links, but global path-based predicators is based on paths. So there are two types of proximity measures: shortest path and cards. So the shortest paths gets the minimum path from node U to V. Similarly, in cards, it gets the path from U to V of fixed length L. So this is the unsupervised link predictors that can be applied for homogeneous networks. Another method for homogeneous network is random walk-based link prediction. So to predict the link between X and Y based on random walks. So I have listed down only three proximity measures for this one. So one of this is hitting time. So the hitting time counts the average steps that a random walker takes to reach from node V, to reach node V from U, and the commute times counts the expectation of steps to read node U from V and node V from U. So it will be the sum of hitting time from U to V plus the sum of the hitting time from V to U. So page rank, I think we already discussed in the class before. So it can walk. It returns a probability distribution. So walk can return to X with probability alpha at every step towards Y. So now we are discussing supervised link prediction. So there are two major components. First is feature extraction, and the second one is classification algorithms. So we can extract features using various methods that we discussed before, such as proximity measures, so local social information and global path information. But what we do is we only focus on the concept of metapath based on schema design. So the metapath can be divided into two: homogeneous social metapath and heterogeneous social metapath. So what is social metapath? If a node start and end with both, like the start and end of a metapath is both user, then this kind of metapath is known as social metapath. So here are some examples. So in the listed example, all you can see is the first node is user and the last node is user as well. So these are social metapaths. So homogeneous are where the nodes and the relations are of the same type, and heterogeneous metapaths are where the nodes and relations might be of different types. So using these metapaths, a set of features can be extracted from the network. So after this set of features are extracted from the network, then we apply some classification algorithms. So for example, SVM is quite popular for this one, so we can use SVM for the classification. So we'll briefly discuss about the clustering in networks. So as you all know, that clustering can be considered as a set of entities that are closer to each other than the rest of the network. So it's like grouping together nodes into cluster according to similarity. So there are different clustering methods based on different similarity measure that we use. So it can be based on topological features or characteristics related to the nodes and edge of the graph. So we are discussing two main clustering in networks. So one is the density-based cluster. So the density-based cluster depends on the edge density among the network. So it depends on the distribution of the edge inside the network. So as you can see in the figure, so the nodes which are densely connected with edges are clustered into one, clustered as one cluster. So another method is pattern-based cluster. So it's not necessary that edge will be the main measure to define the clustering. So the pattern-based cluster doesn't only limit to edge density, but it's based on structure. So two nodes which are not connected to each other or which doesn't have a node edge connecting this, the two nodes can also be classified into one cluster. So for example, in the figure you can see the case of co-citation. So if a set of papers cites a bunch of the same set of papers, but it doesn't have any link between each other, then it's a pattern-based cluster. So these are some measures for identifying clusters. These are some community detection methods that we just mentioned it, but we didn't go through in detail. So yeah, that's all.
Okay. So our survey's topic is link prediction. Our survey topic is link prediction in information networks. So the motivation is very simple. That's in real network, actually in the bars, there are a lot of missing links.
The online students still need to register.
Okay.
Just to get a little far away.
All right.
Yeah.
Okay. So in the real network, actually, it's very sparse. There are a lot of missing links. For example, in a protein-protein interaction network, actually each link needs a biological experiment, which is very expensive to get. So here are very sparse links. Also, some networks, there are a lot of temporal links, which means some in the co-authorship networks, maybe some authors might be connected in the future, but you want to predict from now. So these networks and the previous one needs link prediction problems. And from link prediction problems, we can predict the future links and some other detailed links. In the first examples, you could predict the potential protein-protein interactions and help the doctor to make medicines using your prediction results. And for the second one, you could predict the future co-authorship, or in the social network, you could predict the future friendship. So basically, for link prediction, the method is all the similarity-based or the feature-based. The general idea is that firstly, you define the pairwise dissimilarity between the nodes in the graph. And it is very simple. And firstly, you could use these similarities and select the most similar node to this node and get linked to them. Or you could use these similarities as features and train some supervised models. And the similarity could also be viewed as a kind of feature extraction. The similarity definition could be divided into two parts. First part is local similarity, which considers only two nodes. Or you could define the global similarities. And the global similarities is considering the whole graph. So I will go into the detail. So for local similarities, one most common one is a common neighborhood, which is introduced in the previous slides, the previous survey. And for example, if you want to model X and Y similarity, you just count their common neighbors. And here we can obviously see that there are 3 common neighbors. And for imbalanced, I mean, just as in our lecture for modeling the advisor and advisee relationships, we can use the Jaccard measurement, which is in this graph, we could use the common neighbors number divided by the common neighbors number and divided by the total neighbor numbers. So here, you just use 3 divided by 6 and get a similarity of 0.5. So it's very beneficial to model the imbalanced relationship instead of the balanced one. Also, we can use the degree to normalize the common neighbors. That's divided by the 2 nodes degree. In this graph, in these examples, we just divided by 5 times 4, which is the degree of x is 4 and degrees of y is 5. So another approach is degree-based similarities. The basic idea is we just noted that the node with more connection with others should have more similar than the other nodes. So one of the naive version is just to take the product of these 2 nodes. So in this graph, you just take the 4 times 5 to get the similar one. So in this assumption, actually, it assumes that the halves may have more higher similarity than the one without a half. So actually, combine the degree-based similarity and the common neighbors one, we just use the degree as the weight to sum over all the common neighbors. So in this graph, we can take the weighted sum of B, D, and F and to get the more robust neighborhood similarity. So these are all basic local similarities. And other kind of method is the global similarities, which considers not only the local information, we just consider the whole graph information. So there are also I will introduce 2 kinds of methods. One is path-based similarity. One is random walk-based similarity. For the path-based similarities, actually, you just count from the x to y's passes number. So in these examples, we just count the passes with a length of 2. Since we don't consider the very long passes, maybe it carries much fewer information than the short passes. So in this graph, we just count there are 3 connections or 3 passes each from x and to y. So as illustrated in the previous survey presentations, there's a similarity called cast similarity, which is using a decreasing ways to sum over all the path count. So this is a very robust one. So you could see that most problem methods, those all the problems are all approximating this similarity measurement. Another kind of method is random walk-based similarities. The general idea is that to represent each node using a state diffusion process. So from your random walk, actually from the time of 0, you put a probability 1 to a node I in this graph. There's I here, and after random walk, you could get the diffusion state for each node, and you could use this diffusion state as the feature, or you could use diffusion state to calculate the similarity. And there are two variants covered. One is random walk with restart, and one is local random walk. The random walk with restart actually could bring a more robust way, and local random walk actually is a more efficient way to calculate the real random walk. So these are all similarity-based measurement, but for all the methods, it is quite hard to compute the whole space of similarities. And since for real network, we have millions of nodes, or we have maybe millions of edges. So you need to complete millions times millions edges or links. So from this random walk or actual previous path-based algorithms, you need a lot of time to compute the whole graph. So researchers reduce the dimension using something called the network embedding. And one of the pioneer work is called deep walk. The deep walk, actually, the general assumption is to approximate the cause or the path-based similarities. The assumption is if two nodes in the network, their neighborhoods are very similar, they should have similar vectors. So the target of it is to predict the conditional probability distributions using this formula. And using that one, you can represent each node in the network with a 100-dimension vector. And the computation is quite efficient than before. Also, there's another algorithm called Lion, which is introduced in our lecture, so I just skip it. It's just an extension of the deep walk. So in a real network, actually, each type has an edge type instead of just the homogeneous networks. And one example for the heterogeneous network is the knowledge graph. And there are many embedding methods to solve the knowledge graph embedding. And using that embedding, you could do link prediction or just feature extraction. And I think it's introduced in our last survey presentations. So the first method is called the transition-based model. Its model is just to, its basic assumption is each link in the knowledge graph could be represented as a transition from the starting point to the ending point. And the relationship could be modeled as a vector, which is introduced in trans E, or relationship could be represented as a projection, which is illustrated as trans H. Also, it could be measured by a matrix, projection matrix, adding a vector. So this is called transition R. So another approach is called the score-based model. The general idea is different from the previous one. Is that in each link in the database or in the knowledge base, for each link V1, R, V2, there's a link, and you need to define a score function to directly do the prediction. So given the link in the knowledge graph, you could directly solve it using your maybe neural network or other things to get the similarity. So one method is neural tensor network embedding method. So the basic idea is firstly project each knowledge-based node to a vector, and then use a tensor product taking all node representation and also the edge type representations and do the tensor product, and you get the similarity score. So generally, for feature-based link prediction problems, we cover two parts. First part is basic one, which include local similarity and global similarity. Also, for the modern approaches, we do the embedding in a large-scale network using for the homogeneous information network, we could use the co-occurrence approximation. For the knowledge graph, we could use transition-based method or the score-based method to solve it, to do the dimension reduction.
Okay, so I will introduce the probabilistic model. This model predict links in a different perspective. It's different from previous method which extract features from nodes or edges. This probabilistic model will model the graph with some abstracted representation, and it will predict links based on the representations. So more specifically, we have a set of abstracted representations, and each of the representation will generate some specific graph structure. Assume now we have some given graph. And the first thing we will do is try to find the best representation that maximize some likelihood function, which is defined by the representation and the given graph. And when we got this representation, we could compute its generated graph. And we could compare the generated graph with the given graph. And if generally, if there is a missing link in the given graph, but this link is with high probability to exist in the generated graph, we could predict this link as existing. And on the other hand, if there is a link in the given graph, but there is no link in the generated graph, we could predict as a wrong link. So the first model is called a hierarchical structure model. In this model, the abstracted representation is a tree structure, where each inner node of this tree is associated with a probabilistic value. And each leaf of this tree is mapping to one node to the generated graph. So in the generated graph, there is the probabilistic of the probabilistic that link I is connected to link J is the value associated with the lowest common predecessor of node I and node J in this tree. For example, the probabilistic of a link between node 1 and node 2 is 0.5 because that is the lowest common predecessor of the two nodes in the tree. So when we have this tree structure, and when we are given another graph G, and we could define the likelihood function for a representation based on the tree structure and the given graph. And based on this likelihood function, we could find the maximum point and to find the best representation. And just as I said, when we have this best representation, we could generate the generated graph and compare it with the given graph to find missing links and wrong links. The second model I will present is network evolution model. In this model, the graphs are considered as dynamic, and the graph is represented by a Markov process. And the process goes like this. Each node in this graph will keep advertising its neighbor to one of another neighbor with some probabilistic. And when receiving some advertisement from another neighbor, the receiving node will replace its own entries by the receiving entries. And this process keeps going on until it reaches some stationary status. And what the algorithm does is first it trains the probabilistic that one node will suggest its neighborhood to another neighborhood. And when we have this, when we have trained this Markov process, we could computate the stationary status and compare the stationary status with the given graph to find missing links and wrong links. So that's it. Thank you.
morning. Our survey is about the social data analysis for stock market prediction. So we try to summarize the general method that used in many papers. To construct a prediction model, we need to do some data pre-processing after we gather the data, and after that we try to extract some features. There are three types of features that we will introduce in this survey. So sentiment features, topic features, and credibility features. And after that, we combine these all features to build the forecasting model. So first of all, we know that the social network is very popular today, and every people share about everything on the social network. And so it becomes unstructured data that contain the valuable knowledge. We can see that many papers try to exploit those knowledge from social network to enhance the various type of application. For example, like we can use the social network to predict the stock market movement, or we can use it to forecast like box office revenues of movies. So in the first step, we have to do some data pre-processing. We have many data sources that we can choose to use, but many papers, they use Twitter and Yahoo Finance. For Twitter, they provide us API for crawl the data, like streaming API and search API. For streaming API, we can get the real-time tweets, but for search API, we can go to the historical tweets and get within 1 week, if I remember. So after we gather the data from data source, we have to do some text normalization technique. For example, like do some stop words removal, punctuation removal, or do the lowercase. Or in some paper, they also use the stemming word. So the stemming word is like to map all the inflectional forms of words into the same root form. For example, like we have words like computation or computer. This technique will map those words to the compute, like to map to the root form. And after we do some text normalization, we have to do some filter relevant data, because we know that the data from social network contains many noise data. There are some options that we can use, like do some topic modeling by using LDA, or we can filter by hashtag or cash tag in the tweets. So after we have the data, now we try to extract the sentiment features. So there are two ways that we can use to extract the sentiment information. We can use software to extract sentiment like in the Boolean papers, or we can construct our own classifier for the sentiment classification. If we use to construct the classifier by ourselves, we might need some experts to label the data. And in some paper, they also use the tweets that contain the smiley face or sad face as training data. So they assume that the tweets that contain the smiley face mean the positive feeling, and the one that contains the sad face is mean negative feeling. This way we can reduce the human effort in labeling data, but we have trade-off, because this method might have a less accuracy compared to the labeling data by expert. So after we have training data, we have to train the classifier. So most popular classifier that we see in the paper is the support vector machine and linear regression model. And after we have trained data, so we just evaluate our classifier and apply the classifier for the entire data collection. So now we have the tweets with sentiment label. Next, we have to calculate the sentiment score, because we try to construct the forecasting model. So we have to plot the sentiment information in the time series. So there are some options that we can use to calculate the sentiment score. Like we just average the daily sentiment score, or we can use, in some paper, they use sentiment index or sentiment polarity. So now, after we have the sentiment score, we plot them in the time series. In one paper, they try to test the sentiment information that they just extract from the software to check that this feature is effective for construct the model or not. So they use the Granger causality testing to test the relation between the sentiment information and Dow Jones index. And they also use the self-organizing fuzzy neural network to test the forecasting capability of the sentiment data. So now, after we ensure that the sentiment information we can use in the model, next we have to do some topic features extraction. So the easy way to do is just do the topic modeling. So there are many options that we can use to do the topic modeling. For example, like you can construct the n-gram, use LDA, or you just use JST. Is the framework to extract the sentiment and topic simultaneously. But one framework that we see in this paper, and it seems work well, is an aspect-based sentiment. So first, the general idea is we first extract the topics and then calculate the sentiment score by considering distance between topics and opinion words. So this is a summary of the aspect-based sentiment framework. So there consists of two calculation phases for this framework. First, we try to extract the topics from the consecutive nouns in each sentence in our data and remove the infrequent topics that occur less than 10 times. And after that, we have frequent topics. We start to read each sentence again, but this time we will extract the topics, only the frequent topics, and also extract opinion words from each sentence by using SentiWordNet. So this list of words will give you the opinion words and also the scores of each word. And after that, we calculate the distance between each opinion words and topic in each sentence. So after we have the distance value and sentiment score, we put them together to calculate the sentiment value. So the final result, you will get pair of topic and sentiment value. So next is about the credibility features.
Yeah, so beside the sentiment analysis and topic modeling, we think that we need to take account about the credibility of the social data itself. So based on the paper that we read, we found some definition about the credibility. The first one is from the Castillo in 2011. So basically, they try to find the credibility from its own tweets or the data. And the next one is from Kang in 2012. The first definition is almost the same with the Castillo, but the second is, so they try to model the data by using the tweet as the entity of a graph. So they take account the tweets in social media. So this is some of the paper that we found from the Castle. Basically, they're using some feature extraction from the tweets, like the message-based, and then user-based feature, and then topic-based feature, and also propagation-based feature. The message-based feature is like the length of the message, and then the content of is there any question mark or exclamation mark, and some positive and negative sentiment words. And we also found some paper from Professor Han, the evaluating event credibility in 2012. So basically, they're using the Castillo output and apply some PageRank algorithm to propagate credibility score through the neighbor to get more accurate credibility score. And they also apply some graph optimization. And the intuition behind this is that the credibility score of similar events should be similar. And also, there's some paper that introduced 3 modeling, which is the social model, and then the content model, and they also combine these 2 models into a hybrid model. Okay, and we also find some. So all of this thing is offline assessment. People, some researchers doing this for a real-time credibility assessment. So they, for example, like Gupta and friend, they make some browser extensions that can provide some credibility Twitter in almost real time. And also some other researcher doing Twitter bot, they claim that the accuracy is better than TweetCrit, but the downside is it takes slower to the TweetCrit. And in our paper, we try to put all the features together, the sentiment feature, topic feature, and credibility feature, and select the effective feature, and try some classifier, and then evaluate the data. So for the conclusion, based on the survey that we done, we believe that we can produce some high accuracy of prediction to predict the stock market. Thank you.
Oh. Okay. Yeah, I think we got 4 surveys. Sorry, sometimes the time is limited. But remember, our research project, the time is very tight to make sure you control the time. Okay, otherwise we have to break you out. So there are 2 things. One thing is 9:20 Thursday. You know, we are going to have a second midterm. Another is next Tuesday we will not have a class because our class will be moved down to the reading day. The first reading day, Thursday afternoon, we are going to have 2 sessions. So you just watch our presentation schedule. You come on time. For the reading day, for the presentations, we require everybody to attend at least half of the presentation. That means total we have 6 sessions. You need to register 3 sessions. We still have the attendance sheet. Today, anybody did not get down the sheet, you will need to write it down now. And we're going to bring the new ones for the final project presentation. Okay, thank you.